So good afternoon, I'm Emiliano Merlin from Rome. I actually share my office with Marco. We work on the same data and do the same kind of science. So my talk is going to be kind of complementary to him. I would like to thank the organizers of this very nice conference for having us. Despite we are not directly presenting results which are directly connected to MOND, but we think, well, first of all, we came here to listen and learn, and we did listen and learn quite a lot. But we also hope that these kind of results can be useful for your community, and maybe we can start bridging a gap between theorists and Mondians and these kind of observation hierarchies. So my topic of choice is JWST galaxies at the dawn of the universe. So when I started doing research quite a long time ago, I was actually more interested in formation and evolution of local early type galaxies. So it has been known since, I think, the beginning of extragalactic observation that galaxies basically come in two flavors, can be traced back actually to the Hubble classification. So you have ellipticals on one side and you have spirals on the other side, and then you can call them spheroids and disks, you can call them early and late type, you can call them blue and red sequence. You can have a main sequence of star-forming galaxies and another one of passive galaxies. They are basically the same things. So on the one hand, you have massive spheroids, which are red, and they are intrinsically red because they don't form stars anymore. And on the other hand, you have smaller disk-like structures, which are actively forming stars. How does this happen? Well, in the hierarchical paradigm, which is what the CDM actually scenario predicts, you have a hierarchical formation of structures, so small galaxies form first, and you have smaller galaxies actively forming stars, and maybe they merge at a given time, and merging they trigger a burst of high level star formation, and then some kind of feedback kicks in, and you end up with a red spheroid. And this is public wisdom since forever. Then people at a given time realize that actually stellar feedback is not sufficient to explain the observations, because in order to avoid to end up with many massive galaxies, you need some kind of more exotic feedback like AGN. And then nowadays we have a plethora of possible mechanisms which are involved to explain observations. We talk about starvation, we talk about strangulation, many things used to explain how galaxies cease to form stars, and their gas is no more, it's no more in a reservoir useful to form stars. And all of these are actually, all of these are non-linear, local, microscopic processes which regard the physics of gas, and so you cannot simply model them in an analytical way. You need to make models using numerical approaches, and so people started, of course, well, back in the 90s, and first experiments were actually in the 70s, and then in the first years of this century, there was a boost in numerical simulations, either semi-analytical or fully hydrodynamical, and these we saw already in Stacy's talk on Monday. This is the typical merger tree of one massive galaxies in one of the well-known examples of the first generation of these kind of models, the Lucia. So you can clearly see that galaxies assemble in a hierarchical way, and you have blue small galaxies ending up in a red sequence above. This was 15 years ago or so, then many things happened, and nowadays this is the situation, which is basically the same. So galaxies form this way, and they end up hierarchically forming large structures. This is from the last synergy, and this is the evolution of galaxies on the path, on the color mass diagram that I've shown in the first slide. So all well and good, except that's not the case. We have been knowing since quite a long time that galaxies, early type galaxies, cannot form this way, basically because if you consider their chemical composition and their internal dynamics, they are compatible with an early and short timescale burst of star formation, which must have happened in early times, and while bluer and smaller systems experience a much longer live forming stars. This has been called in many ways. I think the most known one is downsizing. And so this was one of the first, not of the first, but maybe the most important evidences in the past years, which in some way shaded some doubts on the classical ΛCDM approach. And so this part of the, maybe not directly, but I mean this can be seen as a rationale to going observing these kind of galaxies, these kind of quiescent galaxies at high redshift. So we know galaxies come in two flavors locally. How can we find out if that's the case at high redshift? One easy way, not easy, one, let's say, straightforward way is to use the observed colors, so the standard BZK diagram at redshift 2, and then you have to shift, of course, the colors you're using going at higher redshifts. Or you can go to the rest frame colors, and in this case, the typical approach is something like the UBJ diagram, where classic galaxies tend to occupy one specific region in the top left of the diagrams. So this is what people did. And so this is the mass function of the blue and the red sequences up to redshift 2.5 using data from Candace and from Frontier fields made by our group and our colleague Paolo Santini with the UBJ selection. And so you can already see that up to redshift 2.5, which is already like the first, I think, 3 gigayears after the Big Bang, the red sequence, and in particular the massive tail length of the red sequence is already there, and you observe massive and passive objects. Then once you went to the rest frame color space, you can go further and just use the, I mean, if you're using rest frame colors, you're assuming a model, you're assuming some kind of fitting of the observed quantities, and so you can directly use the best fit from your SED fitting to try to single out the objects which are really passive. This is what I did in my work in 2019. I'm not going into detail because I don't have time to do that. But anyway, I try to, I use the canvas data on 5 fields. This is around, well, less than half square degree of area. And I aimed at purity rather than completeness, so I used a quite demanding criteria, set of criteria to single out passive galaxies. Thing is, you can fit your photometry, of course, with different models, and each of the models have a different probability, so you can use the probabilities of the models to exclude objects that can be explained also as star forming because maybe they have obscure star formation going on. So this was my result in that work. We singled out 100 objects in the 5 canvas fields. You can see that most of them nicely fall in the expected region of the UBJ diagram, but some of them fall down here. They are bluer than expected, and of course that's reasonable because we are looking at redshift, I forgot to say, we are looking at redshift higher than 3 here, so the first 2 gigayears after the Big Bang. And here the timescales are so short that, of course, any passive galaxies has to stop its star formation activity since quite short time. So you expect it to have still bluer colors. And then if you look at the mass versus redshift diagram, you can see that these are all massive objects. It is reasonable because, of course, they are farther away and they have to be massive in order to be detected and to be measured in a solid and robust way. But again, we are finding objects of 10 to the 10.5 or 11 solar masses up to redshift 5, and they are passive. They are already evolved. They are already in place at that early periods. So these are the new stellar mass functions obtained with these data again by Paolo, and you can see that up to redshift 4, massive galaxies are there, and then maybe from 4 to 5 they start to be a little less, but I mean you can still find many passive and massive objects. By the way, Marco had shown a slide in which he mentioned the possibility that so we don't know how the star formation rate, cosmic star formation rate was at redshift above 10 or so, less. This was a prediction in this work I made just since I have the best set fit of all my photometric data, I could trace back the star formation expected from the best fit, which are models, and of course, extremely large error bars, but let's say the best fit seem to predict nearly constant star formation rate up to very early epochs. Just not directly related to this, but it was nice to show. Since now we are starting to have evidence of this, not only from JWST, but also from sub-millimeter and far infrared data and radio observations. Then some spectroscopic confirmation started to arrive, and so because this was all photometric, of course. Just for example, by our colleague Corentin Schreiber in 2018, he confirmed these, I don't know, 2 dozen or so objects as being passive and at redshift higher than 3. And the ones marked with the star over there were already in my sample. There were 9 over 20 or so, just because all of the others were not selected, not because the fit was wrong, but because they had some star-forming solution, possible star-forming solution. And so again, since I wanted to single out the very robust candidates, they didn't enter the final selection. And so in a way, my selection is a kind of lower limit of the actual number of passive galaxies in these early years. Okay, and then JWST arrived. Marco talked about this quite extensively. This is a list of the very first papers we released in a rush in the first months. Some of them in the first days when the data came in. I think mine was, the first one was, I don't know if the first or one of the very first public near-cam photometric catalogs that were released, and that was used to single out the 2 galaxies that Marco mentioned. And then we just released a new one for the whole glass plus uncovered field. And you can, it's all public. You can go to astrodip.eu website and download it if you want. There are the images and the photometric catalogs. I started looking at possible passive candidates there, but the game is a bit more complicated here, and I'll explain why in a second. This is one, I mean, just repeating the technique, I found out this guy, redshift 9.5. The fit is there. You can see it's the best fit as a passive object. It's much better than the best fit as a star-forming object, but of course, you see, we have basically no HST data, and we lack also the 090 band in JWST, so perhaps it's just a weird detection. And then these are 2 other candidates that I singled out that way, and then spectra came in, and one of these, the upper one, was kind of confirmed because there are few emission lines. There's the oxygen 3 and the H alpha, which might be caused also by AGN activity, maybe. So it's kind of quiescent, could be, but the second one, which entered my selection as a spectrum, which is full of emission lines, so clearly emitted over and a wrong selection. Why is that? Well, I think the thing is we are going to very, very, very high redshifts where the timescales are very short. And in that case, the star formation is still messy, and it's quite reasonable to think that a sequence of short timescale starbursts happen, and we might find objects which are just in a phase of temporary suppression of star formation. And then maybe you have 2 populations. One is the first older population, which gives rise to the Balmer break, and so many galaxies are identified as quiescent, but then actually star formation is still ongoing, and this messes up the photometric detection. And this is just to show that this has been known since quite a long time. It was once called breathing. Now people prefer, I think, the rejuvenation term. But we know that galaxies, if they are small and they are forming, they are undergoing a sequence of bursting star formation episodes, which may not be related to a final quiescence of the object. And then finally, many other studies came out with either tentative photometric identifications or some spectroscopic identification. This is work by Valentino. Here you can see also the number density of objects which are estimated by him, and there's also my estimate in the middle of the plot, and it's nice to see that it's basically consistent with the new JWST estimations. This is a work by Adam and Bernal, 15 sources in EGS. Again, some of them were in my original sample. And the first spectroscopic confirmation are coming in. So these are 6 spectra by Nana Yakara between redshift 3 and 4. They are all massive and all reasonably identified as passive. One at redshift 4.7, which is actually fit as quenched at redshift 6.7, and it's massive, again by Adam. And maybe one at redshift 7.3, but this is just a post-starburst, and it's a low mass object, so it's more ambiguous. So we need more statistics, of course, and JWST will provide more, but I want to mention Euclid, which was already mentioned in a nice talk by Valentin yesterday. We are directly working on Euclid. Both me and Mark are part of OUMER, so we are the guy who wrote basically the photometric pipeline which are going to analyze Euclid data, which are starting to come in a month, like 2 months. In 1 month it's going to be launched. And Euclid is going to observe basically 1/3 of the sky at this, which is an optical filter 24.5 at theta sigma, which is like something like candles. So it's extremely, it's going to provide a huge plethora of data of exquisite quality. And we also will have 2 deep fields summing up to 40 square degrees, which is enormous compared to candles, which was just, as I said, 1,000 square minutes. 2 magnitudes deeper, with 1 band in the optical, 3 band in the infrared, and then also, of course, a number of ancillary optical data. So I think Euclid will provide many more data to reinforce the statistics on these kind of objects, as well as many other things. I would like to use my final 2 minutes to, first of all, compare with models. So this is what we find comparing the mass function up to 2.5. You see at redshift 0-ish models tend to do good, but of course things get more and more messy and complicated, and basically first of all, they diverge and they predict very different things, and second, basically none of them is able to reproduce what we are observing. This is from the TNG 300 simulations, so it's a huge simulation with 300 megaparsecs per side, and the first passive galaxies here are found to emerge at redshift 4, so anything above is not in the simulations, and we found objects above that. And these were the number density predicted, well, the comparison with the number density that I found in my paper compared with the models, and then the updated version with JWST data and other models by Catriona of these years. And basically none of the models, again, is able to reproduce the observed number density. I just found out about the existence of these simulations, which is, it's claimed to be the first Mondian structural formation simulation, cosmological simulation. So I would very much like to, I don't know if people here can tell me something about this, I would very much like to add this to the comparisons I made before, although we can read there that here too the first structures formulate at redshift 4 or so, and this is somehow in contrast to the prediction by Bob Sanders made in 98. But they claim the thing is the resolution is not high enough here to resolve the formation of galaxies. So hopefully, the message is, I hope in the near future we will have Mondian simulation of structural formation, which can be compared to what we observe. I think I'm out of time, but I think if I can just steal 2 minutes from the question times, I would like to just advertise this thing. I think we need to think carefully about the way we compare observation with models. Because in models, we are provided with true values of things. Particles move around in the simulations, but they have a definite mass, a definite age, blah, blah, blah. And the observation are these kind of messy things, which are noisy photons. And from there, we try to infer their physical properties, and we try to compare to what we find in simulations. Of course, one can, try to account for incompleteness and from, anything, but it's a very complicated game. And simulations have a finite volume, and it has to be carefully compared with the area and the cosmological volume one is surveying. It's complicated. So I'm strongly advertising that people should directly and robustly pass to perform forward modeling of numerical simulations. So there's everything which is needed. You take the models. For each of the stellar elements in the simulation, you have an LCD based on some kind of models, which can be the ones you use for your data fitting. And so from there, you can add noise, you can blah, 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 and you can reach really something which is really comparable to the observation. And we developed a code to do this. My student Flaminia Fortuny did this. It's called Forecast. It's public. We just released the first images. I don't have time to go through the details, but the thing is, it's a particle-based forward modeling code. It takes each stellar particle in a hydrodynamical simulation. It assigns an LCD to the particle. It includes dust. It does whatever it's needed to be done, and you end up with a simulated image like this, which is, by all purposes, similar to a real image, on which you can use the tools that you use on real images to process and perform analysis on real images. So these are the advantage is that, of course, you have realistic morphologies in the simulated images, but also that once you have noise, you end up with something like this, which is fairly different to the previous slide, and it's quite similar instead to what we really observe. So these are, simulations of H and NERCAM bands. And we are just testing, and finishing, we are just testing that everything works fine, seems to do it. So you can, again, browse the website, absolute.eu, to find information about this. Thanks.
Thank you. Stacy for a question. Try to keep it short.
So I do have a question, but I can answer your question. The difference between the new simulations and what Bob predicted is the presence of neutrino hot dark matter. That structure is delayed.
You're talking about the MOND simulation?
Yeah.
Okay.
Yeah. So the structure is delayed there because there's a lot of hot dark matter. And if you just have MOND, that's when you just have structure. And if anything, it does it too fast. So.
But then how do you fit the CMP? Because to my knowledge, that's necessary.
So that's a long answer, so let's do that offline. My question to you is that you've shown all these quenched spectra, and I think you even had a quote that, those things, if you see them at redshift 5, they have to form early and vice versa. So we're seeing all these apparently massive galaxies at high redshift. And I'm sure one of the dodges people will employ is the INAF, to say, oh, it's just the massive stars. But the quenched galaxies presumably have the spectral signature of mid-type stars.
Old stellar population. Well, yeah.
So that seems to argue against, right? You mean you have the descendants that you expect for a normal INF. Is that a fair statement?
Yeah. May I add that I think in some way it's related to the question was made to Marco. We don't have, I'm not sure we have the right models to fit these, because like population 3 stars should enter the game and so on. So it's complicated. It's infancy. It's work in progress. So.
Any urgent question? Because he's used up some of his question time. Okay, I have to give you the minutes.
Sure.
Yeah, that's what I just have a quick point. Like, so in ΛCDM, the formation of galaxies is sort of seeded by cold dark matter halos that exist on very small scales. So if you just go back to the slide where you were showing the MOND simulation, you can see, yes, exactly. So here you can see the right panel at the top is the power spectrum.
Yeah.
And there's a lot of power in ΛCDM on small scales, which is to the right of that plot. In the new HDM, the addition of the neutrinos is not the problem, or not the reason for the conclusions. The reason is a lack of cold dark matter, means that there is very little power on small scales initially, which is why even though you have MOND gravity, it takes a long time for galaxies to form.
No, it doesn't. The growth in pure MOND is exponential. It's very fast.
Yes,
So you start
that's
small and it grows fast.
Yes, that's correct. The growth of the density perturbations is faster, but what is wrong is that the initial amount of power on galaxy scales is, as you can see on the red curve, it's many orders of magnitude below that in the blue curve. And the problem is that in MOND, it's inevitable that there would be no cold dark matter. So I think that's a fundamental problem with the MOND in general.
You don't have to.
It's not a problem. It showed that 25 years.
I believe Alfie has just comment on
Yeah, just a quick comment on that issue. I think there's also a difference in the time associated with different redshifts is different between the two different models.
Okay.
So the Sanders one, the evolution of A is different. You have a different set of sort of cosmological parameters. And I think if you compare the time associated with Z=10 in the Sanders one with the physical time where
Yes,
galaxies form in simulations, it's very similar.
underlying cosmology is slightly different from the 1980s. We have the second. Thank you.